Dummy variables are one of the simplest tools in econometrics, but they have a surprisingly big impact on what coefficients mean. As soon as we move from purely quantitative variables into categories like gender, region, policy status, or season, we need a way to bring qualitative information into a regression. That is exactly what dummy variables do. In this episode, I want to show you how to interpret them, how to avoid the dummy variable trap, how to let categories affect slopes as well as intercepts, and what changes when the dependent variable itself is binary. At the most basic level, a dummy variable is just a 0-1 indicator. It equals 1 when a condition is true and 0 otherwise. That sounds almost too simple to matter, but it is incredibly useful. Once we code a category this way, it can enter a regression just like any other regressor. So categories like female, married, union member, post-reform, or winter quarter can all be modeled inside a linear framework. The key is to name the variable clearly so everyone knows what the one category means. Take a simple wage equation with a female dummy and years of education. If female equals 1, the expected wage is the intercept plus the female coefficient plus the education term. If female equals 0, the expected wage is just the intercept plus the education term. So the coefficient on female measures the difference between women and men, holding education fixed. This is the first big interpretation rule for dummy variables. A dummy coefficient is a conditional difference between groups, not just a raw mean difference across the sample. That immediately tells us something important. Dummy coefficients are always relative to a reference group. In the previous example, men were the omitted category because female was coded as 1 for women and 0 for men. So the intercept described the baseline group, and the dummy coefficient measured how far the other group moved away from that baseline. If we reverse the coding, the fitted values would stay the same, but the coefficient interpretation would flip. That is why it helps to choose a baseline that makes the economic story easy to read. Now suppose we have more than 2 categories, like region. We do not create one big label variable and throw it into OLS directly. Instead, we create separate dummies for the categories, but we leave one out. If there are 4 regions, we typically include 3 dummies and let the 4th region be the omitted baseline. Then each included coefficient tells us how that region compares with the omitted one, holding the other regressors fixed. This K-1 rule is one of the most important practical habits when working with categorical data. Why do we have to leave one category out? Because of the dummy variable trap. If you include every category dummy and also include an intercept, the dummies add up exactly to the intercept column of ones. That creates perfect collinearity. The regression then has redundant information and cannot identify all the coefficients uniquely. So the fix is simple. Keep the intercept and omit one category, or drop the intercept and keep all categories, though the first option is usually easier to interpret. So far, dummy variables have only shifted the intercept. That means the regression lines for the different groups are parallel, but often that is too restrictive. Suppose the return to education differs by gender. Then we need an interaction term, female times education. In that model, the female dummy still shifts the intercept, but the interaction changes the slope. Now the effect of education depends on the group. This is a very common move in applied work because many economic relationships differ, not just in levels, but also in marginal effects across categories. It helps to separate these two ideas cleanly. A plain dummy variable means the groups have different intercepts but the same slope. An interaction means the slope can differ too. So if we only include the dummy, we are assuming parallel fitted lines. If we include the interaction, we are allowing the lines to tilt differently. That is a much richer model. And often it is more realistic, because education, policy exposure, or experience may matter differently across different groups. Here is a good way to read a wage regression with both a female dummy and a female education interaction. If the female coefficient is negative, women start from a lower baseline wage at the reference education level. If the interaction is positive, the return to education is steeper for women than for men. So the wage gap is no longer a single fixed number. It changes with education. That is the big lesson. Once interactions enter, you do not summarize the difference between groups with one unconditional coefficient anymore. Dummy variables are also useful far beyond demographic categories. They are perfect for policy changes, structural breaks, and seasonal patterns. A post-reform dummy can mark observations after a new law takes effect. A quarter or month dummy can capture recurring seasonal shifts. A treatment dummy can distinguish exposed and unexposed groups in policy evaluation. This flexibility is why dummy variables show up almost everywhere in applied econometrics. They are a simple way to let the regression recognize discrete changes in the world. Now take the next step and make the dependent variable binary too. Suppose the outcome is employed or not employed, default or not default, vote or not vote. If we regress that 0-1 outcome on X using OLS, the fitted values are interpreted as probabilities. This is the linear probability model. Since the expected value of a binary variable is just the probability it equals 1, each coefficient tells us how the probability changes when a regressor changes by 1 unit. That makes the interpretation very direct, especially in percentage point terms. The linear probability model is useful, but it has limits. Because it is linear, predicted values can fall below 0 or above 1, which obviously makes no sense as probabilities. It is also automatically heteroscedastic, because the variance of a binary variable depends on its probability. So OLS is not perfect here. Still, the model remains popular as a first pass because it is easy to estimate, easy to explain, and often surprisingly informative as a baseline. So the practical rules are straightforward. Name dummy variables clearly. Always know what the omitted category is. Remember that coefficients are relative to that baseline. Use k-1 dummies when there is an intercept. Add interactions if you think the slope should differ across groups. And when the dependent variable is binary, remember that OLS becomes a linear probability model with both strengths and weaknesses. Those habits will already take you a long way. The deeper reason dummy variables matter is that they let regressions handle qualitative structure without leaving the linear framework. They let us compare groups, model discrete shifts, and describe probability changes in a way that is still transparent. In applied work, that is huge. A lot of real economic questions are not just about how much more of X changes Y. They are also about how outcomes differ across categories and across states of the world. Dummy variables look simple at first, but they force us to think carefully about baselines, comparisons, and what a coefficient is actually comparing. That is why they show up everywhere from labor economics to policy evaluation. Next, we move into heteroscedasticity, where the coefficients may still be fine, but the standard errors start to get tricky.